Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your Zybooks, section 7.4, titled The Rank and Nullity of a Linear Transformation. Now those words may sound familiar, rank and nullity. Remember, the rank and nullity we talked about before in terms of a matrix. Right? The rank of a matrix was the dimension of the column space or the row space. They were equivalent dimensions. And the nullity of a matrix was the dimension of the null space or the kernel of that matrix. Well, you're going to see that that's going to come into play again here. If you recall from earlier sections, every linear transformation can be written as a matrix transformation or has a standard matrix representation. And we're going to see that the rank and nullity of that standard matrix, those are the rank and nullity of a linear transformation. Right? So a lot of this may seem familiar. So remember, the rank of a matrix is the dimension of the column space. The nullity of a matrix is the dimension of the null space. Both rank and nullity can be interpreted and defined within the context of any linear transformation, with results analogous to the results for matrices, right? Similar to the results for matrices. In particular, the rank-nullity theorem holds for general linear transformations. Now remember, the rank-nullity theorem for matrices is that the rank of a matrix plus the nullity of a matrix was equal to the number of columns of that matrix. So we're going to see something similar here, but it's going to be a statement involving the dimensions of vector spaces involved in a linear transformation. Okay, so first we get into some spaces, all right, some vector spaces that are related to a linear transformation. The null space or the kernel, again I've written this up before, you may see the word kernel, K-E-R-N-E-L, when referring to the null space. If you go to look up stuff on your own, you may see the word kernel. And the range of a linear transformation. All right, now remember, the range is the set of the outputs, right? All the vectors in the codomain that get mapped to. All right, so the null space of a linear transformation, from U to V, denoted by the null space of T, right? The null space of the transformation, is the set of all elements in the domain that map to the zero vector of the codomain. So if you wrote that as a set in set notation, the null space of a transformation is all the vectors from the domain such that those vectors map to the zero vector of the codomain. And what we're going to see is that the null space of a transformation is a subspace of the domain. Right, because all the vectors in the null space belong to the domain, so you have a subset of the domain, and it's going to be it's closed under vector addition. It's also closed under scalar multiplication, which I'm not going to go into proving. It's a pretty simple proof. You can read it later. I'm sure they have it in this section. But we're going to see that the null space of a transformation is a subspace of the domain. And then the other space we're going to talk about here is the range of a linear transformation. T from vector space U to vector space V. And it's denoted by the range of T. And this is the set of all the elements of the codomain that get mapped to. All the vectors V in V, such that some element in the domain maps to it, right? there's an element in u and u that exists where t of u equals v. So again, a way to write this in set notation would be that the range of t is all the t of u's, all the outputs in the codomain that have a domain input, that, such that a value from the domain maps to it, right? Such that u belongs to the domain here. And what we're going to see later, and again, I'm not going to go over the proof. You can read the proof on your own or figure out how to prove it on your own. I'm not going to waste time on this, but just know right now, and I'll write this down. The range of a transformation is a subspace of the codomain of V, right? Because all the vectors in the range are from the codomain, right? So it's a subset of the codomain, and it's going to be closed under vector addition, and it's also closed under scalar multiplication. So the range of T, the range of a transformation, is a subspace of the codomain. And once again, the null space of a transformation is a subspace of the domain. Right. Right. Thus, a linear transformation, from U to V that is onto can be equivalently defined as a linear transformation for which the range of T equals V, right? When the range equals the codomain, that is an onto transformation. Right. And we'll also have something to say about the null space and a one-to-one transformation, but that'll come later. Okay. So again, they give you kind of little pictures here. Say this whole big box on the left is U, this whole big box on the right is V. And if you look at where all the vectors in U map to, so they all map to this dark red area, that dark red area represents the range of the transformation, where all the vectors in the domain map to. And then you got this dark blue shaded area in the domain. These are all the vectors that map to, you see they all go to the 0 vector in the codomain. So this blue space would be called the null space of the transformation, all the vectors that map to the 0 vector in the codomain. All right. And as mentioned, all right, again, you can read these proofs. I'm not going to go over these, but just remember what I said before. The null space of a transformation, or the kernel of a transformation, is a subspace of the domain. And the range of a transformation is a subspace of the codomain. All right? So just keep that in mind. And again, you can read through the proof. All right. So finding the null space and the range of a linear transformation. So I'm going to go through this example on paper, and then I'm going to show you. Actually, I'm going to show you two different ways to do it. One is just leave the transformation the way it is, and the other is to look at the standard matrix. All right, and I'll show you how to use the standard matrix to easily state the null space and the range, right? When we put the standard matrix into reduced echelon form. Right, and that's going to involve a lot of coordinates with relative to some basis. All right, so here is the transformation given in that activity. It's from R3 to P1, right? The vectors with 3 components are your inputs. And your output is a polynomial, see the x there to the first power, a polynomial of degree 1 or less. And here's the rule, describing how to take an input and get an output. All right, so first, I'm going to find the null space of this transformation. And again, the null space may also be referred to as the kernel. And if you're looking up other stuff, I'm going to say null space more often because, that's what you're seeing in the text. So find the null space of this transformation, again, labeled this way, null null of t, like that. So what I'm trying to do here, right, the null space is you're trying to find all the vectors from the domain. So all vectors, I'll just call them u equals u1, u2, u3. Find all the vectors from the domain R3 that map to the 0 vector in P1. That map to the 0 vector. Now the 0 vector in P1 would just be the 0 polynomial, 0 plus 0x. So I'll just say 0. Right? Or you could say 0 plus 0x, right? That would be the, but you could just say 0 too, right? This is equivalent to 0 in P1. In other words, we want to solve this equation. When is t of u1, u2, u3, right, when is this equal to 0, right, or 0 plus 0x? Alright, now look at the left side of this. When I apply t to u1, u2, u3, I'm getting this. I'm getting u1 for the constant term minus, and then u3 minus u2 times x, for the x to the first term, this is equal to 0, or, like I said, 0 plus 0x. Now you may recall from a previous algebra class or pre-calculus class you've taken that the only way two polynomials are equivalent all the time is if their coefficients are equivalent. They're for the coefficients for like terms. So this leads me to the following system. If these two polynomials are equivalent all the time, like we're saying, u1, the constant term, must be equal to 0. The constant term over here. And the coefficient of x, this opposite of, or I'll just say negative u3 plus u2, or u2 minus u3. This coefficient of x on the left must be equal to the coefficient of x on the right. That must be 0 as well. And then do you see what we have here? We have a system involving the variables u1, u2, and u3. I'll write an augmented matrix for this system. Down the first column, I'll put the coefficients of u1. So 1 and 0. So again, these are the u1 coefficients. And then down the second column, I'll put the u2 coefficients, 0 and 1. And then down the third column, I'll put the u3 coefficients, 0 and negative 1. And a bar, and then your constants, which are 0 and 0. Right. Now, this is already in reduced row echelon form. Right? This is already in that RREF form. So then I identify my basic variables, free variables. There's a pivot in this first column, so u1 is basic. There's a pivot, right, one of these leading ones in any of the rows in the second column, so u2 is also basic. There is not a pivot in the third column here. So u3 is free. Now you know me, you've seen me do this in other videos. I like to replace my free variables with some other letter. You don't have to, you can leave it as u3. But I'm going to let u3 be the letter t, right, where t is just any real number I want. Right? It's a free choice. All right, then in solving these, now the first equation just tells me that u1 has to be 0. Right? u1 has to be 0. The second equation tells me that u2 minus u3 has to be 0, or u2 minus t has to be 0, and then just adding t to both sides, u2 must be equal to u3, or u2 must be equal to t. And we saw that u3 is also this free variable t that I called it. All right. So, all the vectors that map to the 0 vector in P1 are vectors that look like this. Okay, so that means the null space. Right? So the null space of T is all the vectors from the domain, all the vectors from R3 that look like this. The first component 0, the second component and third component are the same value t, such that t is some real number. Now another way to write this, right? Another way to write this, this 0tt, I could express this simply as t times the vector 0, 1, 1, right? Pulling the free variable out. So another way to express this is by saying that the null space of T is the span of the set with the vector 0, 1, 1. Right? Every vector that maps to the 0 vector in here is a multiple of the vector 0, 1, 1, some scalar multiple of the vector 0, 1, 1. Right? So there's a nicer way, I feel, to express the null space of this transformation. And check it out. Check it out. This is let's see if that's actually true. Now, let's pick a couple examples. All right, so I'm telling you that the null space is the span of 0, 1, 1. Here are some examples. 0, 1, 1 obviously belongs to this. And what does that mean? That means that t of 0, 1, 1 should be the 0 vector. And that would be the case, right? Because you'd have 0 minus and then 1 minus 1 times x. Well, that is the 0 vector. So good there. But any multiple of this, right, would also map to the 0 vector. Here's another vector, 0, 3, 3, right? Just replace t with 3. 0, 3, 3 is in the null space of T. And what does that mean? That means that 0, 3, 3 maps to the 0 vector, right? It would map to 0 minus and then 3 minus 3 times x, and that would be 0. Great. And I could do this all day long, right? Think of all sorts of examples. There are infinitely many vectors in this null space, right? It's every single scalar multiple of 0, 1, 1. All right, and as mentioned before, this null space, right, this is a subspace of the domain, right? This is a subspace of R3. And one other thing I can see from this. Clearly, I hope it's clear to you, this set with the vector 0, 1, 1 is a basis. Is a basis for this null space. And if that's the case, that means the dimension of the null space is 1, right? Because a basis for it only has one vector in it. So this leads me to also the dimension of the null space is 1. And this dimension of the null space is called the nullity, as you saw with matrices. Alright, so we're going to see the word nullity come back later, but I'm just going to throw it out there right now. The dimension of the null space is the nullity of the transformation. You can talk about bases for the null space, because the null space is a vector space, right? It's a subspace of the domain. And we're usually going to be writing our spaces as the span of some basis set of vectors, some set of vectors. All right, so that was the null space, right? All the vectors from the domain that map to the zero vector in the codomain. Now, for the range. So same transformation. Same transformation. So now we're asked to find, the range. Now I feel this is a little easier. Find the range of this transformation, labeled just simply range of t, right? So again, the range of a transformation is just, how the outputs look. What is the set of outputs? So here the range of t is simply this set. The set of all vectors, the set of all, these are all values from P1. It's the set of all polynomials that look like this. As long as U1, U2, and U3 there are real numbers. So U1, U2, U3 are from the domain. Or you could just say U1, U2, and U3 are real numbers, same thing. Now, this is perfectly valid. All right, this is perfectly valid to say this. But I'm still going to try to express this range as a span of some vectors from P1. All right, so do you see how this here, how all the polynomials look? It's just some number plus some other number times x, right? Where a and b, a is u1 and b is this negative u3 minus u2. And you could make any value of b you wish. You could make any value of a you wish. You could get any polynomial from P1 here. But what I'm seeing is, every single polynomial in this output, every single polynomial in the range is a multiple of 1 plus a multiple of x. So to write this as a span of some vectors from P1, the range of t here is the span of the set of vectors 1 and x. So there's another way I could express the range. And if that's the case, the set 1 in x, now these are clearly independent. You can't, there's only two vectors. Remember, when you have a set of only two vectors, they're independent if they're not scalar multiples of each other, which these are not. This is a basis for, the range of t. That's one thing I'm noticing here. And then also, if this is a basis, the dimension of the range of t is 2. And this dimension of the range of a transformation, this is going to be called the rank of that transformation. The rank. So the rank will be the dimension of the range. The nullity will be the dimension of the null space. Now notice that this is also the dimension of P1. Right? This is also the dimension of P1, meaning that the range of this transformation is all of P1. Sorry. The dimension of P1 is also 2. And wouldn't every polynomial in P1 is a linear combination of 1 and x, right? So the range of this transformation is all of P1. And if that's the case, right, if the range of the transformation is equal to the codomain, right, that means that T is onto also, right? We can also say that. Because, every value, every single polynomial in P1 is mapped to by this transformation. Okay, lots of stuff going on there. Now, I'm going to show you an alternate way to do this. Figure out the null space and the range using the standard matrix. Right. So I already found the null space, I already found the range, I'll bring those back later. Now let's do the same thing using the standard matrix. Alright, so hopefully you remember how to find the standard matrix for a general vector space from section, I believe it was 7.2. We need a standard basis for the domain. So remember the standard basis for R3 were these three vectors, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is the standard basis for the domain. And I also want a standard basis for the codomain. And in section 7.2, they were calling that B prime. And, for polynomials of degree 1 or less, every polynomial of degree 1 or less can be written as a linear combination of 1 and x, right? Something times 1 plus something times x. So the standard basis for the codomain is this set with 1 and x here. Oops, not R, P1. All right. Okay. So remember, to find the standard matrix, for a linear transformation, we just need to find the image. What's the output of all these standard basis vectors of the domain, and then translate them to their coordinate vectors relative to the standard basis for the codomain. All right. So what is T of, 1, 0, 0? Well, that would be 1 minus 0x. So that's just 1. But what I'm going to do over here is, change these to their coordinates, their coordinate vector, coordinates relative to B prime, right, relative to the standard basis for P1. And that would be, 1 times 1 plus 0 times x, right? This is 1 plus 0x, so 1, 0. Again, this is relative to B prime. And this will be the first column of my standard matrix. Right. I'll write that here. Right? And this will be the first column of the standard matrix. And then to get the second column, I plug in, the second standard basis vector of the domain. So what is T of 0, 1, 0? So that'd be 0 for the constant term, plus, and then the linear term would be minus 0 minus 1, so plus x, right? Because you'd have minus negative 1x, so plus x. So 0 times 1 plus 1 times x. When I change it to, when I translate that to its coordinate vector relative to b prime, that'd be the coordinate 0, 1, like that. And again, this would be the second column of my standard matrix for representation of this transformation. And then the third one, I plug in the third standard basis vector for the domain. Again, this would be 0 for the constant, and then minus 1 minus 0x, so minus 1x. All right, when I plug into this, and u3 minus u2 would be 1, you'd have minus 1x. And again, translating that to coordinate vector, you'd have 0 times 1 plus negative 1 times x, so the coordinates are 0 and negative 1. All right, so my standard matrix, right, so the standard matrix for this transformation, which was called A back in section 7.2, is this 2 by 3. 1 0, right? 0 1, 0 negative 1. And we can use the standard matrix to figure out the null space and the range of the transformation. Okay. And another thing I'm going to point out here, right? This is a 2 by 3 matrix, right? 2 rows, 3 columns. Point a little tip out to you. The number of rows in your standard matrix is going to be the dimension of the codomain. This is the dimension of P1, right? The codomain. And that'll be the case for any linear transformation when you write the standard matrix. The number of rows in that standard matrix is going to be the dimension of the codomain. And the number of columns in this standard matrix for a linear transformation is going to be the dimension of the domain, right? And the domain here was R3. And this is always going to be the case, okay? So I know it works for this example, but it will always be the case. The size of the matrix, the standard matrix for a linear transformation, will be the dimension of the codomain by the dimension of the domain. Now, what we do is, put this matrix into reduced row echelon form, which it already is. Okay, this is already in reduced row echelon form. So then for the null space, I just imagine the equal 0 on the other side. All right, and this is actually a matrix I had up earlier when I was finding the null space. All right, so to find the null space, just do an augmented matrix with your standard matrix and then the 0 vector, just a bunch of zeros on the other side, and solve that, right? So like we have again 1 0 0 1 0 negative 1 and the bar. Then again, I had this earlier, right? Let's say these were components of the coefficients of some variable u1, u2, and u3 again. And we already saw this, right? u1 would have to be 0. u2 would have to be, again, if I called u3 t, u2 would have to be t, and u3 would have to be t. And so the null space of t is just the span of the vector 0, 1, 1. Right. And we saw this already. Right. I had all that up already here when I went through that whole process of setting up that system and then finding the null space. It's exactly the same. All right. Then for the range. The range we're just looking for those pivot columns of A in reduced or echelon form. Okay, so for the range, look at pivot columns. So again, A, I'll write it one more time here, 1, 0, 0, 1, 0, negative 1. You know, look at the pivot columns. The pivot columns will correspond to basis vectors for the range in A. Right? Pivot columns will correspond to basis vectors for the range of the transformation. So these pivot columns, when you now this is already in, again, this is already in reduced echelon form. Normally, if you had a matrix A and put it in reduced echelon form, you'd find your pivot columns and then go back to those columns in A, but those are the columns here. All right, so the pivot columns here are, 1, 0 and 0, 1, which, when I'm talking about the range, right, the range are vectors in P1. The range is made up of vectors in P1. These are not vectors from P1, but what they do represent are coordinates of vectors in P1 relative to the standard basis. These are coordinates of P1 vectors relative to that standard basis for P1, right, that B prime. And that was that, the set with 1 and x. So a basis for P1, a basis for the range here is going to be, 1, 0 corresponds to just 1, right? 1 times 1 plus 0 times x. And then this other pivot column here, 0, 1, corresponds to 0 times 1, 1 times x, just x. So this is a basis for the range of T. All right, and then again we could say the range of T then is the span of that set of basis vectors. But this has the same number of vectors as the dimension of P1, so this is actually just all of P1, right? So the range of T is P1. And you can tell that again from the reduced echelon form of your standard matrix, which again, I already found all that earlier, right? The range was the span of 1 and x, which is P1. And if the range is all of the codomain, the transformation is onto. All right, so I did it the long way and the short way. Look at this, right? I found the null space and the range using just the standard matrix on a single page here. Now I kind of condensed a bit of the writing, but it was much shorter to do it this way. And I'm going to be doing it this way from here on out, using standard bases for the domain and the codomain. All right. So again, they go through all this junk here, same kind of stuff. Right. Now, they mentioned earlier, if the range of a transformation is equal to the codomain, then that transformation is onto. Well, here's how you can tell if a transformation is 1-to-1 using the null space or the kernel. A linear transformation is 1-to-1 if and only if the null space is only made up of the 0 vector. Right? So if the only vector in the domain that maps to the 0 vector in the codomain, if the only vector that maps to 0 is the 0 vector from the domain, then that transformation will be 1 to 1. You won't have any, two different inputs going to the same output. Right, so again, very easy to tell. When the now here they're giving us the standard matrix for some linear transformation. They're saying T of u is going to be this matrix A times the input vector u, and that'll give me my output. So let's find the null space and the range. All right, so I'll do that again. Now this time I'm just going to pull it up on the calculator. All right, I'm going to enter that 3x4 matrix on my calculator and put it into reduced row echelon form, and I'll be right back when I've done that. You hopefully know how to do that by now on your TI-83, 84. Okay, so I've done this, and I've taken the matrix, the standard matrix they gave me, put it into my calculator, put it in reduced echelon form, reduced row echelon form, and hopefully you see here, only the first column and second column are pivot columns. All right. So what that means is that there are free variables here. All right, there'll be 2 free variables, and the dimension of the null space will be 2. The null space will not just be the 0 vector. So I'll actually go through and find the null space here. All right, let me just go to a piece of paper with this matrix on it. Okay, alright, so here's matrix, the standard matrix A, 3x4. Put it in reduced row echelon form on my calculator there. Now, if you're doing the null space, just imagine there's this bar with some zeros on the other side. And just throw some variables in here, like these are the coefficients, say, of a value x1. These are the coefficients of x2, x3, and some x4. And you're seeing the first column is a pivot column, the second column is a pivot column. So I'm going to have x3 be the letter S and x4 be the letter T. Right? These are my free variables, where S and T are just real numbers. All right, so for the null space, let's solve for x1 here. So x1 is going to be, S plus 2t. Right, because you'd have x1 minus S plus 2t equals 0. x2 would be S plus t. x3 would be S. I already said that, and x4 would be t. I already said that. Now look at these vectors. Look at these components. There are 2 free variables. And I could take, if this was a vector, right, which it is, it'll be a vector from R4, right? The domain of this transformation was R4. So the vectors in the null space will be from R4 like this. I can express this as S times the vector 1, 1, 1, 0. Plus t times the vector 2, 1, 0, 1. Okay, so the null space of this transformation is made up of linear combinations of these 2 vectors. In other words, the null space of the transformation is the span of the set with the vectors 1, 1, 1, 0 and 2, 1, 0, 1. All right, and hopefully you see that the dimension of this null space would be 2. Right, and again, that's called the nullity of the transformation, right, the dimension of the null space, because you got a basis here with 2 vectors. So clearly that's not just the 0 vector, right? It's not the vector with 4 zeros. if the null space is only made up of the zero vector, right? If the solution to this system was only the trivial solution, then your null space would be made up of only the zero vector. It would have dimension 0, and your transformation would be 1-to-1. But since that's not the case, it is not 1-to-1, right? So this statement is true, right? T is not 1-to-1. That is true. All right, stop jumping around. And then what is the range of T? All right, what is the range of T? So back to the paper here. Now, if you want to find the range, again, now I'm ignoring the zeros. Right? So that's only for when I'm doing the null space. Look at your pivot columns and reduce. Take the standard matrix, put it in reduced row echelon form, and then go back to the corresponding columns in the original matrix. Right. So I look at my pivot columns, these two here. Go back to the original matrix, and those two vectors will form a basis for the range. Now the range, remember this was a transformation from R4 to R3. All right. So notice my standard matrix was a 3x4. So the range of T should be vectors from R3. And you're going to see the range is just the span of the set with these two vectors that correspond to pivot columns in my reduced echelon form. So the span of the vectors 3, 1, 2 and -2, 1, -3. All right, and so you see here that the dimension of the range is 2 as well. The dimension of the range is 2, and again that's going to be called the rank of the transformation. Now notice that this is not 3, right? And 3 is the dimension of R3, the dimension of the codomain. So that means the range is not equal to R3, right? This isn't all of R3. All right? And you could have also told me that from looking at the reduced echelon form. You see how the reduced echelon form has this row of zeros? Right? It has a 0 row. That would tell me that the columns of A don't span R3. So all this stuff is coming back, when you look at pivot columns and 0 rows and junk like that. So the statement here that the range of T is all of R3, no it's not. Right? No it's not. It's the span of 2 vectors, a set of 2 vectors. It has a basis with 2 vectors, not 3. Its dimension would be 2. And they go through all that here, I think. Yeah, right? So it's got a 0 row. All right. And then now I've already expressed this. The rank is just going to be the dimension of the range of T. The nullity of a linear transformation is the dimension of the null space of T, or the dimension of the kernel. All right. And here's your rank nullity theorem. Now remember, the rank nullity theorem for a matrix was the rank plus the nullity was equal to the number of columns. If you remember what I said earlier about the number of rows and the number of columns in the standard matrix, I'll bring that page back up. Remember, the number of rows is the dimension of the codomain. The number of columns is the dimension of the domain. So what you're going to see is that the rank of a transformation plus the nullity of that same transformation. Remember, for a matrix, that was the same as the number of columns, but the number of columns is the dimension of the domain. All right, and this is the rank nullity theorem. All right. rank nullity theorem. And you saw that in my last example. All right, let's get rid of all this. All right, the rank was 2. The nullity was 2. 2 plus 2 is 4, which is the number of columns of my standard matrix, but it was also the dimension of the domain. The domain was R4. The rank plus the nullity will be the dimension of the domain. All right, and that's what they're saying here. You know, if T is a linear, again, this is only for linear transformations. It's a linear transformation from U to V, domain U, codomain V. The rank of the transformation plus the nullity of the transformation will be the dimension of U, the dimension of the domain. And you've already seen me do an example of this. All right. I got a lot more here. So let's get to it. All right. So their first example, you know, let T be some linear transformation from R 2 by 2 to R 2 by 2, right? The set of 2 by 2 matrices to the other set of 2 by 2 matrices. Be a linear transformation defined by this, you know, T of x equals A times x minus x times A, where A is this 2 by 2 matrix here. Find the null space of T, find a basis for the null space of T, and find the rank of T. All right. So I'll actually write this one out. All right. Okay, so again, if I'm trying to find, you know, the null space of T and a basis for the null space of T and the rank of T, I'm going to look for that standard matrix. So I'm going to have now B and the B prime. You know, since these are both the same vector space, my standard basis for the domain is the same as the standard basis for the codomain. And if you recall, the standard basis for those sets of matrices were, you know, all those matrices with 1 in one position and zeros in the others, right? So there'd be these would be 2 by 2 matrices that look like this, you know, 1 with 3 zeros there, and 0, 1, 0, 0, and then 0, 0, 1, 0, and 0, 0, 0, 1. Okay. And then what I'm going to do is I'm going to find, you know, the image of all these. Right? So I'm going to call this E1 and E2 and E3 and E4. All right. So what would be T of E1? So I would multiply this matrix, you know, do A on the left. So the matrix 1, -3, -1, 4 times E1 times that 1, 0, 0, 0. Then minus, and then the E1, 1, 0, 0, 0 times A. 1, -3, -1, 4. Alright, so the product of these two, now again, it's a 2 by 2 times a 2 by 2, which would be another 2 by 2. And it'd be, you know, just 1, and then 0, and then -1, and then 0. Right. Right, doing your matrix multiplication. Minus, and then these two together would be, you know, 1, -3, and then nothing and nothing. Alright, so it looks like multiplying on the right by this keeps the first column, and multiplying on the left by this keeps the first row. And then putting these together, you know, 1 minus 1 is 0, 0 minus -3 is 3, -1 minus 0 is -1, and then 0 minus 0 is 0. And then what I'm going to do is I'm going to put it into its coordinates, right? Coordinates relative to B prime, right? So this would be 0, then 3, then -1, then 0. And this will be the first column of my standard matrix. All right, now I'll just write out the next ones. What's T of E2? So again, that would be 1, -3, -1, 4 times, and then E2 is this 0, 1, 0, 0, and then minus, and then E2 times A, and these two. It looks like I'd keep, that'd be 0 and then 1. I mean, this 1 is in the first row, second column, so it looks like I'm keeping the first column here, because it'd be -1, that'd be 0 there, and then -1. Keeping that first column, and then this I'm probably keeping I'm keeping the second row, right? 0. Sorry. First row, first column would be -1, and then it would be 4, and then zeros, and putting those together, 0 minus -1 would be 1, 1 minus 4 would be -3, 0 minus 0 would be 0, -1 minus 0 would be -1. Alright, so then when I translate that to coordinates relative to the standard basis, it'd be 1, -3, 0, -1, right, relative to B prime. Alright, and so I'll do this for the other two and then come back when I'm finished with that. Okay, so here I've written the output when I plug in E3, the third standard basis vector of the domain, and then I change the result to its coordinates relative to B prime. And then I also did this for E4. Got its coordinates relative to B prime. And finally put those columns together, and here is the standard matrix. The standard matrix for this transformation that I probably should have called it something else actually, because they already use A, so maybe I'll call it S instead. Sorry, just realized that. So I'll call this standard matrix S for this transformation here from R2 by 2 to R2 by 2. And notice that it is a 4 by 4 matrix, right? The dimensions of the codomain by the dimensions of the domain, right? Both of them were 4. And then I already went and put this in my calculator and put it into reduced echelon form. And again, let me call this S prime instead of A prime. Sorry about that. Alright, I put this into reduced row echelon form. Now, we're asked for the null space of T. So remember, when you're doing the null space, imagine there's a bunch of zeros over here after some bar in an augmented matrix. Now when you're finding the null space, that null of T, remember these are going to be vectors from the domain. Right? These belong to the domain, which is R2 by 2. So my final result should be a space of 2 by 2 matrices. Alright, so going back to my standard matrix in reduced row echelon form here, I'm going to call this, column, say x1, coefficients x2, x3, and x4. And I'm seeing, x1 and x2, those columns are pivot columns. So x1 and x2 are my basic variables. And then x3 and x4 don't have pivots. Those aren't pivot columns, so those are free. And then, what I usually do with free variables is, x3 I'll call S, x4 I'll call t, right, where s and t are real numbers. And then from that first row, we would see that x1 would have to be 3s plus t. Right. From the second row, we see that x2 would have to just be 3 times s. Right. And then we get our free variables. X3 is s, x4 is t. Again, think of this as a column vector for right now. We're going to eventually translate it back to a 2 by 2 matrix, because remember the null space vectors are 2 by 2s. And if I think of this as a four component column vector, I could break this up into s times 3, 3, 1, 0 plus t times 1, 0, 0, 1. All right. And again, now these are column vectors with 4 components. I would like them to be 2 by 2 matrices. So these are actually coordinates relative to B. Sorry, not B prime. All right. These are coordinates relative to the domain basis, the standard basis. So if I translate back, right, if I go back to having these be matrices, we're going to see that the null space, right, the null space of this transformation is the span of these two matrices. If I convert this back to its corresponding 2 by 2 matrix, that'd be 3, 3, 1, 0. Right, that 2 by 2 matrix, and then the 1, 0, 0, 1, translating that back to a 2 by 2 matrix is 1, 0, 0, 1, like this. Okay, so the null space of this transformation is the span of 3, 3, 1, 0, 1, 0, 0, 1. So any linear combination of these two matrices, when I look back at the initial transformation, any linear combination of these two matrices, when I plug it in, will output the 0 matrix. The output will be 0. All of these matrices and any linear combination of these matrices will map to the 0 matrix. All right, and hopefully you can tell too that the nullity would be 2. Remember, the nullity is just going to be the number of free variables in your standard matrix put in reduced echelon form. There were 2 free variables here. Can you see that the nullity of t would then be 2, right? This has dimension 2, a basis with these 2 matrices, these 2 vectors. And then by that rank nullity theorem, remember the rank of a matrix, or the rank of a transformation, plus the nullity of a transformation is equal to the dimension of the domain. Now the domain, and both the domain and codomain were this R2 by 2. All right, now we know the nullity is 2. The dimension of R2 by 2 is 4. So the rank must also be 2, right? That was the last thing we had to find. What was the rank? And this is the dimension of the range. Now I could also express what the range is pretty easily going back to my standard matrix. Right? So there was a standard matrix S. I put it in reduced echelon form. And again, you look at pivot columns. Look at your pivot columns. And then go back to the corresponding columns in the original matrix. So then the range, right, when I want to write the range out, the range of this transformation is the span of, now again, the range is also, it's a subset of the codomain, and the codomain was R2 by 2. So these are vectors from R2 by 2 as well, 2 by 2 matrices. So I'm not going to write the span of these columns. Right, again, these pivot columns, this column here and this column here. What I'm going to do is change these back to, these are coordinates. These are actually just coordinates relative to B prime. I'm going to change them back to their corresponding 2 by 2 matrices. So the range of T is the span of, this first column, 0, 3, negative 1, 0, would change back to this matrix here, 0, 3, negative 1, 0. And then this other column that corresponded to a pivot, 1, negative 3, 0, 1, corresponds to the 2, would change back to the 2 by 2 matrix. These are the coordinates of the 2 by 2 matrix, 1, negative 3, 0, 1, or negative 1, relative to the standard basis for our 2 by 2. Right. So every single output, right? So no matter what matrix you plug in, every single output of this transformation can be expressed as a linear combination of these two matrices. And so the rank is 2, right? We can see that the rank of T is 2 there, because this basis here for this range is a set of 2 vectors. And we saw that again using the rank nullity theorem. Again, the rank plus the nullity will be equal to the dimension of the domain, which is the number of columns of the standard matrix. All right, and you should be able to do that for any linear transformation. Write a standard, find the standard matrix, put it into reduced echelon form, and then you can easily find the null space, easily find the range. But just make sure that the vectors in the null space and the vectors in the range actually look like vectors from the domain and codomain respectively. That's why I changed them all back to 2 by 2 matrices instead of 4 component column vectors. All right, now they did a little differently. I don't know. I prefer finding the standard matrix, but you can read through that. Okay, so the next part of this, I'm just gonna do this one last example from this activity, and I'll leave the remaining participation and challenge activities to you because they're all similar. It's all pretty much the same. So I'll write out this particular, again, they're telling us it's a linear transformation. We don't have to check that. And then finding, and I'm going to go through the whole thing. Again, I'm going to find the standard matrix, put it in reduced echelon form, find the null space, find the range, so we can easily state the null space, the nullity, and the rank. And you'll see that the nullity plus the rank is going to be equal to the dimension of the domain. So here we have a they're telling us it's a linear transformation from P3, that set of polynomials of degree 3 or less, to P2, the set of polynomials of degree 2 or less, and it's that derivative transformation. Right? So the output is just the derivative of the input. All right, so again we have a standard basis I'll call B for P3. All right, now the standard basis for P3. Every polynomial of degree 3 or less can be written as a number, something times 1 plus something times x plus something times x squared plus something times x cubed. Right? So this has dimension 4. Right? And these 4 polynomials form a basis for P3. And then for right, so that's the basis for P3. Here's now the standard basis for P2, I'll call again B prime, is just 1x and x squared, right? Every polynomial of degree 2 or less can be written as a linear combination of these 3 independent polynomials. Okay, so let's find the standard matrix. Right, and again, you've seen me do this. So I'm going to plug in, 1, the first standard basis vector of the domain. That'll give me 0, which when I translate it to coordinates, that's in terms of, relative to basis B prime, that's 0 times 1, 0 times x, 0 times x squared. This is relative to B prime, right? So this is going to be the first column of my standard matrix. All right, then the next one, T of x, is just 1. So when I translate that to coordinates, that'd be 1 times 1, 0 times x, 0 times x squared. Then T of the next basis vector, x squared, would be 2x. When I translate that to coordinates, that's 0 times 1, 2 times x, 0 times x squared. And then finally, plugging in x cubed, What's t of x cubed? Again, it's just the derivative, 3x squared. Putting that in coordinates relative to this basis for P2. That's 0 times 1, 0 times x, 3 times x squared. All right, again, these are relative to B prime. All right, coordinates relative to B prime. So my standard matrix is a 3 by 4. All right, we have a 0, 0, 0 for the first column, 1, 0, 0 for the second, 0, 2, 0 for the third, and 0, 0, 3 for the fourth. All right. Now this is almost in reduced row echelon form. I mean, all I would have to do is multiply the second row by a half and the third row by a third. So if I put this into reduced echelon form, let's call this A prime, it would simply be this, right? Alright, so let's try to find the null space. So again, you're imagining some column of zeros over here in an augmented matrix. Like I said, I'll call this the coefficients of, say, x1, x2, x3, and x4. And, you know, x1 is a free variable. There's no pivot in there. So I'm going to call x1, I'm going to have x1 be t, where t is any real number, right? So x1 is free. The other columns have a pivot, right? Have one of these leading ones. So x2, x3, and x4, you know, those are basic. So x1 has to be equal to whatever I choose, right? x1 can be anything, t. But from the first row, we see x2 would have to be 0, x3 from the second row would have to be 0, and x4 from the third row would have to be 0. All right. And again, you think about this as like a column vector with four components. This should just be t times the vector 1, 0, 0, 0. All right. So when I write the null space out, when I write the null space of this transformation out, remember these vectors in the null space are from the domain, so these should look like polynomials. So the null space is the span of, and then I'm going to translate this 1, 0, 0, 0 to a polynomial. Now 1, 0, 0, 0, you know, and this is relative to the basis for the domain B. That'd be 1 times 1, then 0 times x, 0 times x squared, 0 times x cubed. So it's just a span of 1. Right. All this is telling me is that any multiple of 1, any scalar multiple of 1, is going to map to the 0 vector in this transformation. And let's see if that's true. All right. Hopefully that makes sense, right? If you take any multiple of 1, you know, 1, 2, 5, 100, its derivative will be 0, right? Every multiple of 1 will have a derivative of 0. Every multiple of 1 will map to 0. And so we have a set here with, you know, a single non-zero vector. So the nullity, right, the dimension of this space is 1. Right, there's only one non-zero vector that spans this space, that forms a basis for this space. Okay. And then, you know, the dimension of P3 is 4, so the range should be 3. All right, remember the nullity plus the range, the rank, the dimension of the range, will be equal to the dimension of the domain. So we're going to see that the rank is 3 in a second. Now again, looking at your reduced echelon form, just take the pivot columns here, go back to the original matrix, look at these pivot columns. The range of this transformation, again, the range, you know, the codomain was P2. These should be polynomials of degree 2 or less. So I'm going to write this is the span of these three vectors, but I'm not going to write the column vectors. I'm not going to write column 1, 0, 0, 0, 2, 0, 0, 0, 3. I'm going to change these back to polynomials. Right? They need to be polynomials of degree 2. And these are all relative to B prime. and b prime was, 1x x squared. So this is 1 times 1, 0 times x, 0 times x squared. That's just 1. Then 0 times 1, 2 times x, and then 0 times x squared. And then 0 times 1, 0 times x, 3 times x squared. All right, so there we go there. So the span of these three, the set of these three polynomials makes the range of t. So every single output, right? And really I could just say x and x squared, because this is just a multiple of x, this is just a multiple of x squared if you wanted. But so every single output here, right? Every single output of this transformation can be written as a linear combination of these three polynomials. And so the dimension of this range, or the rank of t, is 3, as you can see. And that's the same as the dimension of P2, right? The dimension of P2 is 3. So that means the range of t is P2, and this is an onto function. The nullity is not the 0 vector. So that means that this transformation is not 1-to-1. Right? The transformation is not 1-to-1 because the nullity isn't made up of just the 0 vector. But the range of this transformation is the codomain, right? They're the same dimension. So this transformation is onto. Right. So a lot easier to show now whether a linear transformation is 1-to-1 or onto using these standard matrices. And again, you can see that the rank of t plus the nullity of t, right, 3 plus 1 is equal to 4, which is the dimension of the domain, right, the dimension of that P3. And that will always happen for a linear transformation. Rank plus nullity will be equal to the dimension of the domain. Alright, so I basically filled all that stuff in. Dimension of P3 is 4, this is 1, this is 3, cool. Alright. And then I'll leave the other activities to you. You got one more little... I'm hoping this one's obvious by now. If you have a transformation, a linear transformation from u to v, and the dimension of u is equal to the dimension of v, then the following statements are equivalent, right? Meaning that if one is true, all are true. And if one is false, all are false. So t is invertible. I mentioned this before in the previous section on isomorphisms. When they say t is invertible, that means t is 1-to-1 and onto. And if that's the case, then the range of t is equal to the codomain, right? That's onto. The rank is equal to the dimension of the codomain because it's equal to the range, right? And they said the dimensions of the range, domain and codomain are equal, so the rank will just be the dimensions of the two domain and codomain. If it's invertible, it means it's 1-to-1. And remember, if it's 1-to-1, that means the null space is only made up of the 0 vector. Only the 0 vector will map to the 0 vector. And if the null space is the 0 vector only, the nullity is 0, right? This has dimension 0. The vector space with only the 0 vector has dimension 0. So I'm hoping this would have all followed from previous discussions. So they just kind of put it all together. All right. So remember this, I had this up earlier, right? This was a thing earlier. Remember the null space of this wasn't just the 0 matrix? So this is not a 1-to-1 transformation. So it's not invertible. Right. And suppose a linear transformation is onto, then it must be invertible. Well, if they have the same dimension, yes. Right? Dimension 3, and again, if you have a linear transformation where the dimensions are equal, okay. Yeah, then you would have a 3-by-3 standard matrix. And if you put that in reduced echelon form, if it's onto, there'd be no 0 rows, so like every single row, every single column would have a pivot. So it would be 1-to-1 as well. The only, this part, the dimensions are equal. It's onto, meaning the range is equal to the codomain, and if this second statement's true, then all these statements are true. So it would be an invertible transformation. Okay. All right. And I think this challenge activity here, you have to fill in a bunch of blanks in this first level. So again, t from u to v is a linear transformation. Complete the information below. Now, what if if the domain was R5, right? The dimension of the domain would be 5. Now, if the rank were 3, the nullity would have to be 2, right? If the domain was R6, the dimension of the domain would be 6. If the nullity were 4, the rank would have to be 2 to add up to 6. And if it's Rn, the dimension would be n. If the nullity was 6, then the dimension of the range, the rank would be n minus 6, right? So they add up to n. Right. Just rank nullity theorem. Let's see what the other levels look like. All right, so another one, given, fill in the blanks using the rank nullity theorem. Rank plus nullity should be equal to the dimension of the domain. Here's another one with matrix spaces. And here's a different one, but again, easy. Here's the standard matrix. They put it in reduced echelon form for you. Notice there are 2 pivot columns, so the rank would be 2. There are 3 non-pivot columns, so the nullity would be 3, right? Just like your matrices before. Right? But now they're talking about transformations. Real simple. And then you have your exercises. Again, some of these are assigned, some are not. I would still recommend looking at all of them and practicing all of them, and hopefully you get more exposure to the material, get better at it. And you got the solutions to look at if you want. Please try to work on the problems though. Try to figure them out before you look at the solutions. All right, you're not going to learn anything if you're just copying solutions down and not trying. And hopefully this video and other videos I've put up in the past about objectives related to this section, hopefully all these things help you out, and even the other videos by other people that I've put up related to the topics in this section, and reading through the book and taking notes and all the stuff you should be doing as a student. Hopefully all that stuff's helping you when you work on this on your own. And of course, if you have any questions, send me a message and I'll get back to you as soon as possible. And thanks for watching.